Thanks. Speaking with a word of prayer. Again, dear Heavenly Father, we thank you for quizzes that help us learn. I just pray that it would always be productive in here when we do it. And I just thank you again, Lord, for your many blessings to us this day, Lord. In your name I pray. Amen. Okay, so I guess I should run through the quiz right quick. This is our a sub k. So if I take a sub k plus 1 over a sub k, that's going to be k plus 1 to the k plus 1 divided by 3 to the k plus 1 quantity squared. And then I multiply that by the reciprocal. The reciprocal here is 3 to the k squared divided by k to the k. All right, so that, we've got to do some algebra. So this is k plus 1 times k plus 1 to the k. We got our 3k squared up here, divided by, of course, k to the k. I'll put that first. I'm going to do a little side work here. So notice that k plus 1 quantity squared is what? K squared plus 2k plus 1, right? So this 3 to the k plus 1 squared can be rewritten as 3 to the k squared times 3 to the 2k plus 1. Like that. Let's see here. So what do we get? We've got, we can group things together. We've got k plus 1 over k to the power k. That and that goes together. And let's see here. Then I've got k plus 1, right? Divided by, let's say, 3 to the k, 2k plus 1. Right? Now, of course, the 3k squareds, those reduce, those cancel, right? Like I'm canceling these guys and these guys. All right, so what's the deal with what remains? Of course, this can be rewritten 1 plus 1 over k to the k power, and this again is k plus 1 over 3 to the 2k plus 1. All right, so good news. This goes to e, and this goes to 0 by an application of L'Hopital's rule if you don't see it immediately. K plus 1 over 3 to the 2k plus 1 by L'Hopital's rule, infinity over infinity, extending k continuously. That's 1 divided by 2 natural log of 3, 3 to the 2k plus 1 by the chain rule. And of course that goes to 0. What's that? You got to go to 0?
Could you have done the root test?
I don't know.
That's what I...
That might also be a way to do it. So this one here goes to, this goes to 0, right? So therefore, by ratio test, let me call this thing S. S converges by ratio test with lambda equals to 0, which of course is less than 1. Could I have done the root test here? Possibly. I'm not. Let me try it out for a second here. K to the power k over 3k squared. I'm supposed to look at the kth root of that, right? So, of course, that is the natural enemy of k to the k, which is not bad. So this is k to the k to the 1 over k upstairs divided by 3 to the k squared to the 1 over k. Ooh, I think I like your solution better. And this is 1 over laws of exponents, 3 to the k. You might make me start to believe in the root test. I like that. That's better.
Why did you say k over
Oh, is that k?
Yeah.
Oh, I'm an idiot. Thank you. So, z L'Hopital, infinity over infinity, 1 over log 3, 3 to the k, and then that goes to 0. Hence, what do we call it? Rho? Rho equals 0, and S converges by root test. So it doesn't matter. You go either way. Yep. I can't hear you. I'm sorry.
You end up with 0, but did not show the L'Hopital's. So you still set that.
If I didn't put L'Hopital's rule, but I said it went to 0, would I still?
That's like after you cancel out, you split it using the ratio test. Not
He just means that k over 2 to the k.
after you
That's
cancel
zero.
out.
Well, in a problem like this, if you're sure about it, if you know, if you understand what you're doing is this, I'm kind of okay with it. But it depends on the problem. If I say to show your work, then I want to see the L'Hopital's rule. Yeah.
Is that the only way to get it? 'Cause I got that answer. I
Root
got
test over here is another way to do it.
I got convergence by the ratio test.
Yeah.
But I didn't end up with 0. I had E over 3.
Well, you miscalculated something, I'm pretty sure, because unless I've made a mistake here, I don't.
Yeah. No, I
Yeah.
looked at it differently, I guess.
Yeah. You probably have deceived yourself in this algebra, most likely. Okay, this one I think is root test.
Yeah.
So is Miss Becky?
Yeah,
So you just this root test all the time?
I did both of them. Yeah.
It's a big fan of the root test. I guess I can't discount it. I mean, you do have a point. It does work. I mean, I got to find an example which forces us to do ratio test. I chose poorly, I see. Anyway, that is, of course, root k minus root k minus 1. Infinity minus infinity equals what?
0.
No, equals you do some more algebra. Okay, so this is, so what I would do is I would take this and I would multiply by root k plus root k minus 1 over root k plus root k minus 1. See what happens with that. That gives me k minus parentheses k minus 1 by the algebra over root k plus root k minus 1, which, by the way, is equal to, k's cancel, 1 over root k plus root k minus 1. Hey, that just goes to 0. So that's this series converges by the root test with rho equal to 0. What is it?
Okay, well, I just.
Now, did you guys get stuck on how to deal with root k minus root k minus 1?
Yeah.
Yeah. But now you know, right?
Yeah.
So
So you couldn't assume that they should both go to infinity and therefore it goes to...
infinity minus infinity is an indeterminate form. It could go to 0, it could go to 3, it could go to infinity, who knows? You can't, you see something of the form infinity minus infinity, you can't know what that works out to until you do further analysis. It's an indeterminate form.
Because the k minus 1, the minus 1 would just become insignificant eventually.
Right, I mean, you don't know which one's going to win,
Right.
basically. I mean, once we do this, we know that they cancel out, right? Which intuitively kind of makes sense here because they're the same function, so after a long time, they should cancel. But, you know, that kind of intuition can lead you astray. Okay. All right, so let's get to the new material. So today we're talking about absolute convergence. What is the definition of absolute convergent? A series is said to be absolutely convergent if the series formed by the absolute value of the terms converges. All right? So, for example, on the other hand, a series is conditionally convergent. What's that mean? If the series itself converges, but the series of the absolute value diverges. In other words, a conditionally convergent series is one which is convergent, but not absolutely convergent. Just to give you some examples. Let's see here. So the sum minus 1 to the n over n squared, n equals 1 to infinity. So this would be like 1 minus 1/4 plus 1/9 minus 1/16 and so forth and so on, right? Well, I guess we don't have a technology yet to show that this is convergent, but you'll have to trust me when I tell you we will soon have a theorem which shows us how to prove this is convergent. Trust me anyway, it's convergent. Turns out. So I'm have to, yeah, this is an alternating series. It turns out this is convergent, all right? And if you take, what's the, absolute value of what does absolute value do to minus 1 to the n? It's like the natural enemy of it, right? It just kills it. So that's just 1 over n squared. In other words, so sometimes you might hear people call this the top one, the original series. This here, a sub k equals to minus 1 to the, sorry, I'm using n here for a second. A sub n minus 1 to the n over n squared. If it makes you more comfortable to always use k, you could put k here. I just wanted to mix it up for a second here. This is the alternating p equals 2 series, all right? So the absolute value of a sub k, a sub n here, is just this, right? But this is the p equals 2 series, right? So of course, this converges for what it's worth to pi squared over 6, but who cares? Apparently I do, I've mentioned it twice. But anyway, convergent. And actually, it doesn't matter that this converges, for what it's worth. Like absolute convergence, what does it require? It requires that the series, the absolute value, the series formed by absolute values of the terms converges, right? So the second fact here is all it requires, is all that's required logically to prove that this series is absolutely convergent, all right? We will soon learn that absolute convergence implies convergence. Here, let me prove that for you. Theorem. Absolute convergence implies convergence of a series, of course, is what I'm talking about. So here's the proof. If you have the sum of the absolute value of a sub k equals to L for some real number, right? In other words, suppose that the series converges, the absolute value of the series converges, rather. How is the absolute value of a sub k related to a sub k? If a sub k is positive, it's what? It's equal to it, right? If the term is negative, it's minus a sub k, right? So you can pretty easily see that this is less than or equal to a sub k, which is greater than or equal to minus a sub k, right? So what's that show you? This shows you that 0 is less than or equal to the absolute value of a sub k plus a sub k, which is less than or equal to what? 2 times a sub k. So then what?
Oh, you got it.
Are you assume that AK is any number?
All I'm assuming here is that the series formed by absolute value of a sub k, yeah, could be positive or negative. The point is it's absolutely convergent.
I thought that the absolute value of AK is larger than or equal to AK.
Well, less than or equal to, it's equal to, right? That's included in the cases.
Because AK can be
This is or. It's either less than or equal to. It's equal to.
like AK is negative and
Oh, am I got it backwards? Oh, I've got it backwards. I'm an idiot. Thank you. Yeah, I think we're about to chase a rabbit there. I'm sorry. I'm an idiot. So a sub k is less than or equal to. Okay, that's what I want. I'm sorry. I'm an idiot. So this, what you were just saying, this is less than what? Right? And then down here we can put, okay, yes, I'm stupid. All right, so now that we got that, then what? This implies 0 is less than or equal to a sub k plus the absolute value of a sub k, right? Then what? So what he does in the text is he rewrites a sub k equal to, what does he say? He says a sub k is equal to, now this is a little bit tricky, but he says it's equal to a sub k minus the absolute value of a sub k plus the absolute value of a sub k. Now he's added 0 here. What's the purpose of doing that? Check out this inequality here. What does this say? This says, by direct comparison, right? The sum of a sub k plus the absolute value of a sub k converges. Right? How do I know that? Because 2 times a sub k is twice a convergent series. Right? So this a sub k plus absolute value of a sub k converges. Right? So then when you look at this, oh, I'm an idiot. I can't do anything right today. So we wanted what? We want what here? We want plus here and minus there. Yes. All right. So this, right, converges. The series converges. And this itself doesn't, I mean, this has to converge to 0 as it happens by the kth term test, but more to the point, the sum of a sub k plus the absolute value of a sub k converges. And to the series formed by the absolute value of a sub k was assumed to converge, right? So hence, the series formed by a sub k converges. All right. Sorry for the stumbles at the start of that. So this is a very nice result. If we have absolute convergence, we automatically get convergence. All right? So one of the things I would point out is the ratio test, right? Comment. We can use ratio test for the series a sub k with a sub k not equal to 0 for all k, right? If we test a modified ratio test, I would say. I say modified because that's not how your book states it, but basically we would look at, let's say, the absolute value of lambda, right? We look at the absolute value of a sub k plus 1 divided by the absolute value of a sub k. Usual song and dance, right? If this is less than 1, if this goes to, goodness gracious, eventually I'll get it right. If this goes to, absolute value of lambda, so to speak. I don't really want to call it absolute value. Let me just say it goes to lambda. You want to call it something else, whatever. The point is that if this is less than 1, what does that say about the series? It says that the series of absolute values, right, the corresponding absolute value series converges. So in fact, if we use ratio test, right, on the absolute value of the series rather than the terms in the series itself, we can test for absolute convergence. If you look at other calculus texts, sometimes they state the ratio test with absolute values in it, and then the ratio test is said to test for absolute convergence. They just do that altogether. There's other calculus books which present it that way. Anyway, does that make sense? If we use ratio test on the absolute value of the series, then we test for absolute convergence. All right. So that brings me to the major result for today. I guess I should show you a conditionally convergent example. The standard example is this one. If you look at the sum k equals to 1 to infinity of, say, minus 1 to the k plus 1 over k, all right, this is 1 minus 1/2 plus 1/3 minus 1/4 plus dot 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 dot. It turns out, for this reason, that this equals to the natural log of 2. So this is a convergent series. Yet, the absolute value of the series is what? Yeah, it's the harmonic series, exactly. This diverges. It's p equals 1, right? It's a harmonic series. So this is an example of a conditionally convergent series. It's really the quintessential one. All right, yes? Do telescoping series only conditionally converge? Is that your question? I don't think so. Not always. I believe so, because I think what we worked out the other day was that you can rewrite any series as a telescoping series. So since I know some series are absolutely convergent and some are not, that would say to me that I could take a given, but this is not a telescoping series either. This is an alternating series. Although, I see the similarity. I see what you're saying. They're both kind of got this plus minusing going on. So it's kind of a intuitive jump, I think. I see where you're going with that. There's a theorem by Riemann. Riemann's rearrangement lemma. Or theorem, I forget if it's a lemma or it's a theorem. Anyway, it's Riemann's result. Says you can regroup or rearrange, if you like, terms in a conditionally convergent series, and make it converge to any real number. Yeah, lemma. It could be theorem. I'm not actually. Anyway, it's a result due to Riemann. If I take the numbers, right, and I do things like, for example, I could do 1 plus 1/3 minus 1/4 plus dot 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 dot, and just push the half way on out there. I forget how it's done. It's not that. It's not that kind of thing. Like, it's just reordering them, just shifting them around and putting one before the other. You can get different cancellations, And you can make it work out to whatever you want. It's fascinating, but also kind of off topic in here. But my point to you is conditionally convergent series are dangerous. Things simple that you think wouldn't make a difference, like rearranging the terms, can change the thing it converges to. It's very weird. Yeah. This does not happen for absolutely convergent series. Absolutely convergent series, you can move the terms around that are being added. It doesn't change the outcome. This is the big difference between conditionally and absolutely convergent things. We will use absolute convergence. Yes, we will. Will we ever rearrange it to make it come out to a different thing? If I could find the right homework problem. I mean, does he have a homework problem on that? Let me see here. He might have one. In Stewart's calculus, I think he has how to make it how to rearrange it to get it to come out to like 3/2 log 2 instead of log 2. Let me see if he probably has it. Let's see here. Well, it's not jumping out at me. He might not have it. We need a refund. You guys spent a lot of money for this book. I tell you what, I'm going to tell you what, I'm not happy about this. Oh, there's a rearrangement. Well, he comments on it on page 600, though. So maybe he's got an example. He shows two different rearrangements of, well, anyway, who cares? I mean, I care, but not enough to keep talking about it. All right, let's go on here. Yes. All right. So sorry, I'll stop distracting myself. This is the major theorem for today, and also a definition. If a series has the form, if you can write a series in this form, like here, this is called an alternating series. So an alternating series is one which is formed by a positive and then a negative term plus a positive plus a negative plus a positive plus a negative. Or if you're like, just thinking in terms of positive terms, plus something minus something plus something minus something, and so forth and so on forever and ever. It doesn't really matter that it starts with something positive. Like you could start with a minus and then go minus plus minus plus minus plus versus plus minus plus minus plus minus. We don't care about that. That's not what makes it. That's not part of the definition. But this is an alternating series. This theorem, by some of my fellow grad students back in the day, they called this the wishful thinking theorem. Because what this really says is that if you have an alternating series and the kth term goes to 0, it converges. Now you guys have a very bad habit of trying to extend this theorem to other things like this. You're like, oh, well 1 over k goes to 0, therefore this series converges. Is of course not true. Because this is not an alternating series, and so the alternating series test does not apply to it. In fact, it diverges, even though the kth term goes to 0, right? But for an alternating series, magic happens, and it is sufficient that the kth term goes to 0, given that you have a, as long as you've got a decrease, you do need decreasing. Decreasing is important, so we need decreasing sequence of positive terms. All right. So here's the proof of this. Some proofs we should go over. This is one of them. So we assume. So of course, first of all, this symbol right here. You guys are going to ask me about this as soon as you notice it, right? What is this? If and only if, right? So I could replace this with double arrows, sometimes like that. It's a biconditional statement. So first of all, this direction is easy. This is by the kth term test, right? Remember that? We proved that if a series is convergent, it must be that the kth term goes to 0. So the forward implication is just kth term test. What's interesting, of course, is the converse direction. So this way. So now we'll suppose a sub k goes to 0, where a sub k is positive, and a sub k plus 1 is what? It's decreasing, right? So a sub k plus 1 should be less than a sub k, for k equals to 1, 2, and so forth and so on. I guess 0. I started at 0, didn't I? K equals 0, 1, 2, and so forth and so on, forever and ever. So we suppose that data, all right? And what he says is he plays some games with the even and odd partial sums, right? So let's try to play these games with the book and see if we can follow them. This is pretty much the proof. You'll find this argument in other books. It's kind of like the standard argument. It's instructive, I think, to go through it. It gives you a little bit more insight as to why this theorem works. So the even partial sum, 2m, right, is, what is that? Well, that's a sub 0 minus a sub 1 plus what? Plus a sub 2 minus a sub 3 all the way on out to a sub m, 2m minus 2 minus a sub 2m minus 1, parentheses, and then finally the 2mth term, right? So there's the partial sum of even index. Now, here's a formula that relates the 2m plus 2th partial sum to the 2mth partial sum. How is it? What do you do? To get to this from that, what do you got to do? Right, we have to add the next two terms in the series. So he writes it at kind of a, yeah, I mean, I would say it's minus a sub 2m plus 1 plus a sub 2m plus 2, right? But he just rewrites that in a slightly more suggestive way as 2m minus parentheses a sub 2m plus 1 minus a sub 2m plus 2. Why do you do that? See, the reason he did that, what can we say about the term in parentheses? The terms are decreasing, right? We need to use that somewhere. This is not like just for the sake of writing it. This is a necessary condition for this theorem to go. Yeah, exactly. This is a positive number, or possibly at least not negative, right? So what does that say about this? We're taking s sub 2m plus 2, we're taking s sub 2m, and we're doing what? We're removing a positive number from it. What does that say about the partial sums themselves? S sub 2m plus 2 is less than or equal to s sub 2m, right? I guess he has a strict inequality. I'm not sure. Oh, they're positive terms, right? Since they're positive terms. And I think, but he doesn't say, does he say strictly? Oh, right. Remember the talk we had at the start of all this? I've forgotten. In my lingo, strictly decreasing. Strictly decreasing, which means that I've written it correctly. It's not less than or equal to. So this is not a non-negative number. This is a positive number, which makes this a decreasing sequence. All right, just to be precise. What does this show? This shows that the sequence of partial sums of even index is a decreasing sequence of positive numbers, right? So check it out. We have shown then that the sequence of, so basically you've got this sequence, let's call it b sub m equals to s sub 2m, right? What can we say about this sequence? This is a decreasing sequence of positive numbers. So what can we say about that then? Right, it's bounded below by 0, right? That's, I mean, we said it's positive, right? Bounded below by 0. Therefore, S sub 2m converges to L as m goes to infinity. So then what? How about the odd terms? How about the odd partial? I mean, is that enough? We also have odd terms, right? So S sub 2m plus 1. I wrote a 2. What's wrong with me? S sub 2m plus 1 is equal to what? It's equal to S sub 2m minus A sub 2m plus 1, right? So the odd partial sums are related to the even partial sums in this simple way. So what? So this converges, right? And this, what happens to this? As m goes to infinity, we're assuming that this goes to 0, right? So think about it. This must go to L as m goes to infinity. Now we have to use something in here we haven't proved, but you'll find entirely intuitively reasonable. If you have a sequence, right? And you can prove that all of the odd terms in the sequence go to L, right? The subsequence of odd terms goes to L. And if you can prove the subsequence of even terms goes to L, it follows that the total sequence also goes to L. All right? I could spend 20 minutes proving the epsilons and n's of it and stuff, but I think that's a reasonable jump, right? So we've proved that the even and the odd subsequences of the sequence of partial sums both converges to L. Consequently, the sequence of partial sums converges to L, which is what? Say what? That's to say, this series converges, right? And there's a little bit more that you get that I'll talk more about next time. We even get something that's really, really nice. The error, well, I won't write it out, but the error, if you truncate this at like 7, right? How far that is from the truth is no larger than A sub 8. I think that's a fantastic theorem. So, you know, if I look at the sum, for example, minus 1 to the n over n equals 1 to infinity, and I say that that's equal to 1 minus 1/2 plus 1/3, approximately. Well, that's not, I mean, that's an approximation, right? So this would be working, that works out to what? 5/6, right? So what's the next term that I've neglected? The next term that I've neglected is a 4th, right? So the alternating series estimation theorem says that 5/6, that the series minus 5/6 is going to be less than 1/4. I'm telling you, we will soon develop tools to work out that the series here, this thing, is natural log of 2. You can easily calculate that the natural log of 2 is about 0.693, or 0.693, yeah, and 5/6 is what? Minus, what is 5/6? That I don't know. 0.844444? 44444443333? I don't know what it is. You guys help me out. 0. You can leave me out. You can leave me out dry here. It's fine. 0.82, roughly speaking, right? Anyway, you can see that that is about 0.12-ish. And of course, that's less than 0.25. So there's the alternating estimation theorem in action. It gives you such a alternating series are so precious because we can describe the error in truncating an alternating series at a finite term in a very simple way. The alternating series are fantastic. And I'm sorry I didn't do more examples of them today, but it's probably my own stupid fault for giving you so long on the quiz. I won't make that mistake again. I'll shut up. Thanks, guys. Oh man, I wanted to be the power series tomorrow.